Recording is on.
Yes. Okay.
Yeah,
Please.
so the topic of my talk today is time-sensitive applications of in-network machine learning. I received my PhD degree from the University of Oxford in engineering, and my focus mainly focused on the intersection of networking, in-network computing, and machine learning. So my main focus is about time-sensitive applications of in-network machine learning. I will introduce what is in-network machine learning later. Yeah, so the agenda for today's talk is like this. I will first introduce the problem and the motivation behind the research, previous approaches and their limitations, and then I will introduce my research, including the hypothesis, the contributions, and the main approach with the utilization of in-network machine learning. I will also include some use cases for the evaluation and to illustrate my findings. And in the end, I will have some reflections and outlook for this field and this direction in the future. So for the problem, so in-network machine learning can play a very important role in ultra-low latency scenarios across various critical domains. For example, in intelligent transportation system, in-network machine learning can enable real-time traffic prediction, anomaly detection, and adaptive signal control by processing sensor and vehicle data directly within the network switches. It can reduce decision latency. And another example is, for example, in smart healthcare, particularly in like remote surgery or emergency diagnostics, in-network machine learning can support immediate response through in-network inference, minimizing the delay between patient monitoring and accurate control. And in smart factories, in-network machine learning can detect, for example, equipment faults, quality anomalies, or robotic coordination issues directly within the network edge, ensuring fast reaction and preventing downtime, all while avoiding the delays of crowd-based inference. And we have also many other time-sensitive applications that demand very rapid responsiveness while existing machine learning systems fail to deliver. So that's how I think in-network machine learning can make a difference here. Here is some related works. So we can see apparently some works mainly focused on machine learning side, but their platform is always the server and data centers. But there are other works that mainly focused on like low latency side, but they always use like, for example, FPGA, SmartNICs, but we can hardly see any machine learning aspects like involved within this kind of works. So I think the hypothesis of my research is running machine learning directly within the programmable network devices. Here we called it in-network machine learning. And we believe that this approach can accelerate time-sensitive machine learning applications. So we can both have the low latency aspects, we can both involve the machine learning models to utilize their intelligence. The contributions is as follows. First, I designed a new methodology for prototyping time-sensitive machine learning applications. I designed in-network solutions for low latency financial forecasting and then the real-time fraud detection. So these are two main use cases for the research. And the fourth one is that I developed novel data structures in programmable data planes and in-network feature engineering, all like I will illustrate throughout the introduction of the use cases. So what is in-network machine learning really is the offloading of machine learning inference to the network. So traditionally, machine learning inference are based on the servers. Now we want to remove it and move it into the network devices itself. So that's called in-network machine learning. There are several benefits that in-network machine learning can bring to us. The first one is location. So network devices is already exist and it's within the network infrastructure itself. We don't need to add more additional hardware or devices into it for the in-network machine learning to work. And also it's along the path And in our machine learning, if it's offloaded into the programmable network devices, different data source, their data flows comes within the device. We can do the data aggregation and the information processing within the devices itself, and then goes to the end servers. And second benefit is the latency. Not only does the programmable network devices, they can process information quicker than the servers, but also here we want to introduce early termination. So for example, the data source come to the network devices, processing within it, and then goes back to the destination. It doesn't need to go to the server for further processing. So in a lot of use cases, we can see that in-network machine learning has a shorter data path. In this case, it can reduce the latency, not only in processing time, but also in communication time. Third one is the load. So today, the increase, we see increasing volume of data and information and computing burden are all on the servers. But now we want to offload some of the burdens into the programmable network devices, because there are a lot of idle computing resources within it that has not been utilized. And also network devices, they provide high throughput and high power efficiency aside from low latency benefits. So yeah, here is some typical target platform. So one is programmable switches, one is a DPU and the smart network interface cards. We call it smart NICs. And then we also have FPGAs and low-end devices. So in-network machine learning can all work and function in these kind of platforms. Yeah, the research first has some contributions to in-network machine learning community. So here are three works. Planter, we developed use cases, conducted researches, and I helped with paper writing and the revisions. So this is rapid prototyping for in-network machine learning framework. We also have Easy and Dink, mainly focused on hybrid deployment of in-network machine learning and distributed in-network computing. So these are Changgang's work. Changgang is leading authors of all these three works, and he already gave a talk for this community before. And my research, the main difference of my research comparing to Changgang's research is that mine is more focused on the use case side, the application side. So I apply in-network machine learning into the time-sensitive applications to utilize the low latency provided by the programmable network devices. Yeah, as we can see, so for a lot of previous in-network machine learning works, they mainly focused on data intensive tasks, so leaving time-sensitive applications unexplored and unaddressed. So here is how my research can fill the gap. So here I will introduce the first use case. It's called market prediction from the market by order data. So MBO here is market by order, is an order-based market data fit specifying the price for a certain security at which the trader is willing to trade, as well as the quantity of the shares. So we have high-frequency traders. They already operate trades with very high frequency, but they want higher intelligence to aid their decision making. We also have some algorithmic traders. They always trade in mid or low frequency, but maybe they want lower latency to get to a better decision at a quicker time. So that here in our machine learning, we believe it can sit in the middle and function in the programmable network devices and provide solutions for both sides. So yeah, I just use machine learning classic problems in financial fields, which is to predict future price movement of a single stock. So basically, this is a classification problem. The price after, for example, 100 ticks can go up, can go down, or can stay stationary. So there are three classes. And this use case has been included in Planter's early report as an extension use case. And the table shows the machine learning performance both within the switch and with the server as our baseline. And we try different machine learning models such as SVM, decision tree, random forest, XGBoost, naive Bayes, all these machine learning models. We find that actually the performance is nearly the same. So models trained with machine learning with MBO features perform no better than random classification on the switch. So this indicating the efficiency of the input features. So the next step we would think about is how to optimize our feature, how to improve our feature. We find that if we draw features from the market by order MBO, it's not stateful. It doesn't have the info. It doesn't include the information of what happened in the past, and it cannot give a better insight of what will happen in the future. So this is not the ideal features we want. Then we move our attention to limit of the book. We call it LOB. It's stateful and it can provide better features for our decision making. Here is the illustration of how a limitable book works. It's basically you can treat it as a real-time summary of unmatched orders for a certain security that are used to trade at specific or better prices. So when new orders come, you will either execute it with the resting orders within the limit of the book, or if there's no like proper execution here, you will just rest in the limit of the book, waiting for maybe future orders come and execute and match together. So this is our first use case. We introduced lobbing. So lobbing is LOB within the network. It's a solution for providing high frequency and high accuracy stock price movement prediction by building the limit of the books within the programmable switches based on high frequency market data feeds. So as you can see in the figure, so when the market like MBO data comes from the stock exchange, it goes to like in the traditional solution, it goes to the switch, which is already within the network infrastructure for the traffic forwarding, and then go to the server for machine learning inference and the decision making. But now I want to move the machine learning models within the network itself, within the programmable switch, so that in our solution, in our design, the data feed comes to the switch. We build a whole limit of the book and update it based on the real-time machine learning, real-time MBO data. And then we do the decision making, and we directly send our decision back to the stock. So as you can see, the communication time between the switch and the servers are reduced. This is the system design of lobbing. We consist of components on server, control plane, and the data plane. So first on control plane, we have our training data, like historical data of a single stock. We have some like training configurations. So the first step is to train a machine learning model. And then we want to map that machine learning model within the network itself. So in this process, basically is we generate a P4 code, which the P4 programming language is like a language that is designed to processing data within the network. Here we have like three components of in the program. One is related to machine learning. One is related to how to build the limit of the book. One is like standard code, basically like designed for like packet forwarding, those basic functions. After we map the machine learning models within the network, so in the real time in the data frame, in the data plane, when the real-time market data comes, we build the limit of the book first, and then we do the feature extraction from the limit of the book, and then we do the machine learning inference. And all these functions we implemented can co-function with the standard P4 program. So it will not affect the like basic functionality such as traffic forwarding. So we use programmable switches as our hardware. We implement using P4 on BMV2, Tofino, and Tofino 2. These are three different kind of software switch and hardware switches. Here is the innovation. So innovation, I think, is mainly like two parts. One is I designed the novel data structure, which is the in-network limit of the books. And the second one is I designed two in-network algorithms of constructing and updating limited book within the network devices. There are a lot of challenges, of course. For example, the P4 programming language, it does not support loops. It does not support some data types, for example, the float data types. It costs a lot of like stage and computing resources and memory resources if we want to, for example, simply compare two values. And also, we have limited access to registers, and we have a high cost of, for example, we want to implement it if-else conditions. So if we use Python or any high-level language, we can do this very easily, but we are using P4 to do the data processing within the network devices itself. Yeah, here these are all become very high-cost challenges. So the solutions are, for example, we use loop unrolling for lack of loops. We use packet recirculation. For example, if in one data plane, we cannot read some values from the register, do a lot of complex updates and computation based on it, and then write it back. We cannot do it in one data plane. Oh, sorry, in one data pipeline. So we utilize the mechanism of packet recirculation. We use one pipeline just for reading and updating, and then we recirculate back to the devices and go through the pipeline again just for writing the updated values back to the registers. So here we can overcome the challenges of limited access to registers. And we also want to optimize our algorithm so it can fit into the network devices within the limited, for example, number of stages and the memory requirements. Yeah, so that required optimization of the algorithm itself. Here I give some examples of, for example, this is the exemplary illustration of how machine learning, how MBO messages can be used to update the limit of the book. What are different scenarios, and what is our workflow of update the limit of the book based on MBO data? What's like different? For example, we have buy side, we have sell side. We have an order to buy a certain asset. We have order to sell a certain asset. Whether the current best buy price or best ask price, how does it compare with the price specified in the order? So we need to consider all these conditions and do the corresponding updates. So here is our algorithm. I won't go into the details, but you can find it in our paper. Here is the algorithm to update the limit of the book based on the MBO data within the hardware itself. So yeah, so the evaluation side, we first evaluate the machine learning performance, right? We use the data sets of provided by Nasdaq's historical data feeds. It's open sourced. And we run lobbing, which is our solution, run on switches with limited size models, while we run another benchmark on a server using like scikit-learn with unlimited size models. And we find that even if like lobbying within the hardware run with limited size of models, utilize limited number of features, the loss of machine learning performance is minor. And also we found that for tree-based ensembles, for example, like random forest, XGBoost, including decision tree, it's very effective. We can see, like we can barely see a loss in terms of machine learning performance. Here we use accuracy F1 score ratio for machine learning performance evaluation. These are very common metrics, and we tested different machine learning models in our evaluation. And also we want to test networking performance. So we already know that machine learning performance, our solution has little difference compared to the server, but we want to know what's the networking performance what's the networking benefits that our solution can bring compared to the servers. The results is very promising. We can achieve microsecond scale latency even under resource constraints and with packet recirculation. we achieve 3.2 terabits per second throughput, meaning we can process 1.45 billion messages per second. So lobbying uses fewer features and smaller machine learning models, but it can provide huge latency benefits. And then we evaluated based on a hybrid deployment setting. So a hybrid deployment setup combines a small model with switches and a large model on end-host servers for better performances. And the evaluation results is here. We found that the 45% of the traffic and 38% of the total potential transaction value can be processed within the switches, while we can ensure that the average change in error rate remains within 3% relatively to server benchmarks. So in this case, we can combine both servers and the hardware. We can combine the benefits provided by both and limited our error rate to minimum, and we can offload a number of traffic and potential transaction value from the server within the hardware. So basically, for hybrid deployment, we use we call it confidence threshold, confidence level. So for machine learning, for one decision make, if we do it on the server, for example, we use a tree ensemble model such as random forest, XGBoost, it will provide a confidence score for each decision. So if the confidence score is high, we can offload it into the switch. If the confidence level on the switch is low, we can forward it into the server for further classification. So in this case, we can both assure high accuracy, but also ensure low latency, because part of the traffic and the transaction value can be processed within the switch with already very high confidence level, so that it does not need to go to the server. So here, after this work, we also explored in a further extension work that how we can use like advanced features, not just, for example, in lobbying, we just use the volumes and the price levels and the bid-ask spread. For example, this kind of features to aid our decision making in machine learning models. But now we want to focus more on in-network feature engineering, how to develop higher level features based on living notebooks, including the order flow imbalance. So, and we want to support both mid-price focusing and also the volatility movement forecasting. So we also extend the tasks. And also we integrate the new data source, Lobster, which is a very famous data source, containing a higher volume of data feeds. And the results, we find it in better machine learning performance than previous use cases, because we used advanced features, of course. And then we significantly lower latency by 64% to 97% compared to previous CPU, FPGA, and the SmartNIC based works. Here is the algorithm we implemented in the hardware that to generate higher level feature, for example, order flow imbalance within the hardware. Now comes the second key use cases. Is not in finance anymore, is in the fraud detection. So we introduced Mind, which is a solution that conducts machine learning-based detection for fraudulent transactions within the programmable devices. So real-time notification can enable the security team, for example, in a financial entity or in other entity, to act immediately, minimizing the financial losses and preventing the escalation of fraudulent activities. So these are the system design of Mind. It's very similar to lobbying, just the use cases are different, the data is different, the algorithm offloaded within the network devices is different. But as you can see, the general workflow of how to train a machine learning model and map the machine learning model within the network devices is the same. So we implement our solution using three different transaction data sets. The innovation here, aside from the previous use cases, is that we use new enablement models. For example, we support SVM and naive Bayes this time. And also we introduce new evaluation metrics. These two metrics is mainly utilized, very useful in the problem where the number of samples in different class are very imbalanced. So, for example, in fraud detection field, uh, for example, in financial transaction, there are a lot of in our data set. There are a lot of samples, of course, are illegal, but just a very few numbers of the transaction are illegal. So there is class imbalance issues here. So we want to use the metrics that can better used in the evaluation of the class imbalance problems. And now we also use new target devices, for example, NVIDIA Bluefield 2 DPU, because they have encryption and the decryption functionalities. So you can better simulate the real-time, real-life scenarios where for banks or other financial entities, the financial transactions, they will be encrypted and decrypted within the flow. Yeah, here comes also a lot of challenges, and we come up with different solutions to solve it. Here is the evaluation for this use case. We managed to achieve line rate throughput of 6.4 Tbps and the microsecond scale latency. We can process over 800 more transactions per second, reduces the latency by over 1300 per transaction versus the server-based solutions. And we can achieve 99% of server benchmarks accuracy and 93% of their F1 score. So the conclusion is we can offer substantial savings in the number of servers by utilizing enabled machine learning solution, and we can lead to reduced costs and energy consumption while providing a better customer experience. Because if you can prevent the financial loss quicker, you can help reduce the loss for the customers. So the lessons learned is based on those introduced use cases is that we managed to implement and design the complex data structures and engineered features efficiently deployment them into the programmable data planes. And secondly, the enabled machine learning delivers high performance in low latency scenarios. The networking, or we say system performance, is better than the server-based setups, and only minimal reduction in machine learning performance observed. And also, we want to know that the model type and the size are mainly limited by hardware resource constraints in this work. There are also future directions. First is we can expand this in-network solution into more time-sensitive applications. For example, smart manufacturing, smart transportation, gaming, and AR and VR. And also we can develop advanced in our machine learning techniques. For example, we can offload more algorithms in deep learning and reinforcement learning field. We can focus on machine learning model scalability. We can focus on hardware compatibility to new P4-enabled devices, for example, a DPU, IPU. Yeah, and thirdly is that we can collaborate and engage with industry. For my research, we collaborated with Oxford University Innovation and Oxford Science Enterprises on licensing and the venture opportunities. Yeah, and I think these kind of opportunities we can partner with the real world scenarios and companies to try to find out how to move our research from the labs into the industry. Yeah, here is some publications during my PhD. If you want to find out more details about the use cases and the enabled machine learning solutions in time-sensitive scenarios, you can try to look at the papers. Yeah, thank you very much. Is there
Yeah,
any
thank you very
question?
much, Shimping, for a very nice presentation and actually the work. Thank you very much. I have a couple of questions, but first of all, let's see that is there any question? Mm, okay, so regarding running Lubin, maybe it's better that I bring the chat here. Regarding running Lubin on switches,
Yeah, yeah.
are
You said
these
that you are running the algorithms on the switches, right? So I just wanted to ask if what kind of switches are these? I was thinking that on the SmartNICs we're supposed to run a lot of algorithms using their processors and use soft switches instead. So are these hard switches with processors on them, or some other kind of
Yeah,
technology
first
that is on
we,
them?
yeah, thank you for your question. So first we implement the prototype into the BMV2. It's a software switch. It's basically for prototyping and just to prove our prototypes can theoretically work in hardware. And then we use Tofino and Tofino 2. They have processors. They have like real life like resource constraints, and we implement our prototypes and offload it into Tofino and Tofino 2. They are the hardware switch designed by Intel, and they can prove that our solutions can actually run on like off-the-shelf hardware, programmable hardware in real world.
I see. So those are software switches, correct?
Yeah.
Yep. Good. Yep.
so? Thank you for the question. Um, actually, uh, so again, thank you very much for the very nice talk. Um, I have a question regarding classification. I mean, this classification that we have the results are, for example, the accuracy. It is like we are predicting the market that is go up and down. So this shows that how much our prediction is accurate.
Yes.
Okay, great. But then, actually, because I'm not deep into this research, is it like so we because I see that you said that so we have the companies that actually they're like really using ML for predicting the market and do the real trading.
Mm.
Okay, interesting. Um, and then actually, my another question is that. So the regarding the models, is it because you mentioned that okay, so we have the features for a specific, for example, share.
Mm.
So usually, I mean, how is it like? We have like one models that it supports a couple of shares, and then oh no, we need to have a couple of models running on the switch for supporting different shares.
Yeah, so basically our solution now is just a proof of concept. So basically we just use one model at a time to support like one single stock. And I
So
think in the
there's
future,
one model and one share.
yes. So, but I think like in the future, if the hardware like limitation, resource limitations can be released a little bit, or higher advanced hardware has come out, we can use like multiple models for multiple shares, like simultaneously work. But now it's
Yes.
basically the hardware limitations. Yeah.
Okay, but then this hardware limitation, even like in the real use cases, so we can have only. I mean, do you have any roughly, for example, how many shares that we can focus that we can support? So, but probably it depends on the size of the models. I mean, like,
Yeah.
yeah,
Basically, I think we can use because Changgang's one of Changgang's work is about like a DINK. It's basically we can utilize because there are not only one switches.
we can have
If there are a
distributed.
lot of switches, like we can offload one model within each switch and one model for one share. But those switches can co-function together so that we can, for example, predict the future price movement of 10 correlated stocks at the same time.
Yeah.
So I'm thinking about like the level of 10 or 100.
Yeah. Okay. Very nice. Very nice. And then, and actually, I have also one more question regarding the this encryption and decryption, and also using the like DPU blue field. Is it
Yeah.
like can reduce the latency if if you have it like running on the blue field?
Yes, it can reduce latency, and also we try to use like the NVIDIA Bluefield DPU's encryption and decryption process so that it can better simulate the real world scenarios. But yeah, the communication time and the computing time can also be reduced if we use Bluefield too.
Blue filter, yeah, okay, yeah, yeah. Thank you very much.
Yeah, thank you.
But I don't know if there is any other question.
Thank you.
Yeah. So if not, I can stop recording our session.